Okay, so yeah, so one thing too is I am going to try and record this, and I'll give out the recording and also the slides, and also I'll try and edit out. If I feel free to ask a question, and I'll try to edit out voices just in case someone's uncomfortable with having their voice in a recording. One thing too is I was actually looking at the meetup description on the way over here, and I said a lot of stuff in that description. I think probably do like 10% of what I said. It turns out that it's actually like kind of a huge topic. But the first one, the first sort of infinitesimal also I'm gonna like try and like be here so I can like, face you guys. So if something embarrassing happens up there, you'll have to try and keep a straight face so I can't tell. This guy his name is Kepler, and he wrote a book at one time called The New Solid Geometry of, I'm guessing this is wine, maybe this is barrels. And evidently what the story was that these wine barrels had some sort of spigot or something here, and the way that these merchants would determine how much to charge you for filling up the barrel was they would put a stick in here, and they would stick it all the way to the corner, and however much of the stick they could fit in, they would say, well, that must be proportional to the volume of the barrel, and so we'll charge you based on that. And Kepler thought about this and said, well, I think that's not quite right. You can have different size barrels that you can fit the same size stick in. And so he wrote a book about it, about how to actually determine how to charge for your wine. And he had these various methods for determining volumes and areas that described in his book. And kind of as like a warm-up, he showed how to find the area of a circle, which I think now is like maybe like one of the most common sorts of arguments involving infinitesimals that maybe even get presented to calculus students. And he has this, I kind of like just kind of put this in for historical interest. We're not really going to analyze this diagram. This is from his book. I don't know what this thing is here, but this is a circle. And the idea, we can just read what this historian said about his computation, is that, so he says that, by the way, I copied and pasted this from a website which had a typo for circumference everywhere. So if they see the recording, they were going to know that I copied from their website. Of the circle, he says that the circumference has as many parts as it has points, each part forming the base of an isosceles triangle with vertex at the center of the circle. So he's talking now about a triangle like this. The circle is accordingly made up of an infinity of small triangles, each with its base on the circumference and with altitude equal to the radius of the circle. Replacing these triangles by a single triangle with a circumference as base, the area of the circle is thus given in terms of the circumference and radius. And so what he means is that this is a triangle here, and then some other triangle, for example, this one here, you can slide it in over here, and then another one you can slide in over here, and you can keep sliding in these triangles, and the last one's going to be this really thin one. And you're going to make up a triangle with the base, the circumference of the circle, and height, the radius, and that should give you the area of the circle. And so just to say that, I guess a little bit more detail, we know that a triangle has this area, base times height over 2. And so just by the distributive law, if you have a whole bunch of triangles with different bases, potentially different bases, then you can add them up by summing over the bases. And so Kepler is imagining that the circle is made up of triangles with an infinitesimal base, such that when you sum them all up, you get the circumference. And then he says, okay, well, I put that together, and I get that the area of the circle is pi r squared. And so then the main question is, how to make sense of this, because, he's, on the face of it saying that, this thing here, which is actually not a triangle, just to spoil it, this is not a triangle. He's saying that it's a triangle. And the question that I kind of want to address in this lecture is how can you make this kind of reasoning precise? Well, still using infinitesimals. Like, if you've taken calculus, you can make this precise by just eliminating any mention of infinitesimal. But it turns out infinitesimals are useful, they're powerful, and we want to keep them around. So I will tell you, oh, right. Yeah, there's actually like 3 separate falsehoods involved here. and they all have to be dealt with. The first one is that what I just said. He says the area of this thing, which is not a triangle, is this triangle. The second thing is he wants to compute the area of this triangle, so he has to make two further lies. He has to say that this length is equal to this length, because he knows this length, and he has to say that this length is equal to this length. So there's three separate things that are just not true, and that we have to figure out how we can make true. So without first saying, so I said justification here, but like I realized after I made this slide and after I was too lazy to change it, that it's not really a good word, because I'm not telling you why this is good justification. I'm just telling you what is the reasoning by which you can discard these small differences. And the heuristic that is, I would say, well known maybe to physicists and engineers, is that you can discard a difference E if, even compared to your dx, that difference is infinitesimal. And so what I mean by that is, so we know, because we've split up the circle into infinitesimally many pieces, or infinitely many pieces. We know this is already infinitesimal, but we know that the area that we're discarding by turning it into a triangle is sort of even more infinitesimal, because that extra area is contained within this rectangle, and it has one of its sides are infinitesimal, and the other side is some other infinitesimal, because this function is continuous, which means that small changes result in small changes of the function. So like this is a small change of the function, so its value has to change by a small amount as well. So this is kind of the way you justify throwing away this area, at least if you believe that such differences can be discarded. And yeah, so just to, I guess, orient you, so I'm going to try and give some more examples of arguments involving infinitesimals, and I'm going to try and work towards, so this can actually be made into a theorem if you say everything correctly, and this theorem will still involve infinitesimals. It won't involve removing them or replacing the limits. And I want to develop enough stuff that I can say what this is, give sort of a precise statement of this theorem.
Oh, Michael, excuse me. You be willing to take questions while you're talking, or save them all for the end?
Yeah, no, yeah. Yes.
While you're talking, it's fine.
Yeah, okay. But you didn't have a question.
I
thought you
had
a meta question.
General point of information.
Yeah. Cool. So here, I'm just trying to say a little bit more precisely what it is, the heuristic, which I'm sort of working towards. And this is not like this isn't, I've just made this name up. This is not a real thing. But the argument structure that I'm trying to work towards making precise is, if you have some sort of arbitrarily divisible process, like, for example, dividing up a circle into small wedges, you're allowed to make those divisions infinitesimal, and then discard differences that are even infinitesimal compared to the size of your division. Okay. So the next example that I want to give is an example from Archimedes, and it was right before this talk. It was an example that Tom was just complaining that people make mistakes on presenting, so I'm feeling great about this. And one thing which is sort of interesting is that people didn't know that Archimedes used infinitesimals in his thinking until relatively recently, like 1906. And this is the New York Times newspaper clipping of like the find of his book that explained his thinking of how infinitesimals can be used to derive various things. And I think that, like, in keeping with the sort of Greek mathematician thinking, he didn't view infinitesimals as a rigorous way to prove anything, much like people today sometimes don't. But he definitely understood their intuitive value, and he wrote in, I think these are maybe letters to Eratosthenes, although I'm not exactly sure. He wrote about his ways about deriving his results about the volume of spheres, the areas of parabolas, all sorts of stuff, and how he thought about it with infinitesimal slices of things and so forth. And a lot is thinking in according with this this phrase, like mechanical methods, involves what's called the law of the lever. And the law of the lever says if you have a seesaw or lever, and you have two things on it on either side, some weight here and some weight here, and this one is this distance apart, this one this distance apart, then it'll balance if the product of the weight and the distance are equal. And today this is something like, there's no net torque on it, something like that. Or maybe there's no moment or something like this. Okay, so as an example for how he would use such a notion to solve problems, so let's suppose that he wants to find the area under a parabola. So this is y equals x squared. Oops. From 0 to 1, and he knows obviously the area under a triangle. So this is y equals x. This is also a base 1, height 1 triangle. So okay, so fine. So what's the trick? So as you might imagine, so he slices these up into very thin slices. And so on. And he observes that you can actually balance the corresponding slices on the lever if you put them on in a particular way. And what does this mean? So if you take the slice, so consider the slice in the paraboloid that starts at distance x, for example. So let me maybe zoom in. So it starts at distance x, and it goes to distance x plus dx for some infinitesimal. So he can kind of view it as a rectangle with width dx and height, x squared. And so what he imagines now is that if I take such a thing and I hang it from the lever at a distance 1, so now this is supposed to be the same slice, it'll exactly balance with the corresponding slice from the triangle that starts at x. And the reason for that is that, so this rectangle, so it has width dx, height x squared at distance 1, and the corresponding slice from the triangle has width dx and height x, and it's at distance x from the fulcrum. So this will balance. And notice here, so this is where he is like, he's doing the same shenanigans that Kepler did, in that like he is ignoring this extra part. And it's with the same sort of justification that that Kepler used, in that this change from here to here is very small. So this area which we're ignoring is even smaller than this. And so we can just neglect it and just think of it as a rectangle.
How do you get the right side again? The right side of the equation, dx times x.
So there's a slice, say the slice here is from x to x plus dx.
Okay.
And so this is the area of the rectangle, dx times x.
Yeah.
And the distance from the fulcrum is x.
Oh, okay. The distance from the fulcrum is x.
Yeah, so it's crucially, like that's the trick. Like he's using the fact that the triangle is lying on the lever, so it's like its mass is at different points spread out on the lever. That's the trick of this argument. Thank you for asking that. So yeah, so now, okay, so that's an interesting observation. And now how does Archimedes proceed? He says, okay, well, I can take every slice, hang it here, and then balance it with a slice here. So that must mean that I can actually do it all at once and hang the entire paraboloid here. and it will balance. Sorry, that's a paraboloid. And it will balance with the triangle resting with its mass spread out on the lever. Okay, so that's good. And so now to complete the argument, Archimedes wants to now hang the triangle as well at some place. And so Archimedes also knows that if you have something spread out on a lever, you can replace that mass with you can consider that mass to be concentrated at the center of mass, the centroid. So he can move this triangle down and hang it from a place if he can figure out where the centroid of the triangle is. And he actually knows, I think this is not related to infinitesimals, but I think he knows, I think maybe probably Euclid knew this. He knows that the centroid of the triangle is at the place, let me remove this. He happens to know that the centroid of the triangle is at the place where these medians intersect. And so the median is the line from a vertex to the side bisector on the opposite side. And he also happens to know, he knows a lot of things, so that's handy. He knows that this is 2/3 of the way. So these are all, like, this is 2/3 of the way to here. And this is 2/3 of the way to here.
Excuse me,
And this is 2/3 of the way to here.
The point where the lines meet, like if you balance the triangle like on a pinpoint or something, it would balance.
Yeah.
It would just be totally horizontal. It would totally balance there.
Yeah, that's right. Yeah, I think that, like, what I read is that Aristotle thought of it that way. He thought of the center of gravity as like it's the place where if you suspend it, it'll have like no tendency to rotate.
Just like flat.
Yeah. And so, like, that's also how he knows. So he has this, like, sort of very practical way of finding the center of gravity, where like you hang it from various places, and then so you hang it, and then like you have like a sort of plumb line or something like that, and then you can draw a line, and you know the center of gravity is somewhere on there, and you hang it from someplace else, and you have another line, and then you have a plumb line, and like where they intersect is the center of gravity. Maybe you do it a third time because there's some error here. And so, right, so this is the center of gravity here. So, and you can also sort of see, like there's going to be, because this is bisecting it, it's going to be equal areas on either side, which is why it's going to balance if you sort of hang it from here. So anyway, so this is 2/3 of the way to 1. So this is 2/3 here. This is 2/3. And now we imagine that we can hang the triangle here. And so now Archimedes uses, let me just erase some of, oops. Let me erase some of this. Archimedes uses the law of the lever again, and he says, okay, the area of the parabola, which is what I want to know, times 1, its distance from the fulcrum, is equal to the area of the triangle is 1/2, times 2/3 is its distance from the fulcrum, equals 1/3, which is correct. It's also the answer you get by integration. So that's, I think the questions about that, that's basically his method. This is law of the lever method.
Wait, so the relationship of the areas again is what? I'm sorry.
So he's again using the fact that so W1 x1 equals W2 x2. So here W1, the weight 1, is the weight of the parabola that we want to find out. X1, the distance of the parabola to the fulcrum, is 1. W2 is the area of the triangle, which we know to be 1/2, because this is 1 and this is 1. And X2 is 2/3, which we know from this centroid median method. And so A times 1 is 1/2 times 2/3, which is 1/3. And so the area of the paraboloid, the area under the paraboloid must be 1/3.
So the area of the triangle is 1/2, and the area of the paraboloid is 1/3.
Yep.
So that the paraboloid area is 2/3 of the triangle area.
It's
Wait.
4, 1. Well, no, it's 2/3. Wait, no, 4/3 or something.
That's all right.
Other questions? Cool.
I was also going to say, I mean, maybe you already know, maybe we'll get to this.
No.
He used, Archimedes also used a totally different method to prove this very similar thing. where he would fill in the spaces with triangles and smaller and smaller triangles, which created an infinite series. So he arrived at the same, conclusion. Method totally not involving physics at all, just involving mathematics.
Yeah, I did see that. Like, it's like, yeah, that was pretty remarkable. So like he proved these things with these infinitesimal methods that were already extremely clever, and then he like said, okay, well I know the answer now, but now I have to find some totally different clever method to actually write down a rigorous proof.
Right.
And so I had no idea about this before researching for this talk. But yeah, what Tom is talking about, like, so he said, okay, well now I know the area of the paraboloid. Let me just come up with a totally different ingenious way to prove it to people. And so I actually don't, maybe you know Tom, so I think he's like, so he's approximate. Yeah, go ahead. Yeah.
Isaac Newton did something very similar with this Principia, where he used what we now recognize as calculus and come up with everything.
Yep.
And then he, but if you read the book, there's no calculus in there. It's all based on triangles, basically.
Huh.
It was a very small process. He didn't think anyone would take calculus seriously. So
Yeah. Yeah, I read that like we think of like Principia as like, oh, that's what introduced calculus, but like he didn't really, that wasn't his goal. Like he didn't want to promote or explain calculus at all, really. He was just trying to explain, these other things, his gravitational law and stuff like that.
So you said the area of the triangle is 1/2, but the area under the parabola is 1/3?
Yeah, that's right. Mm-hmm. Yeah. And yeah, so what I read, so so Newton and Leibniz didn't actually make it into this talk. It's a huge history of math history of infinitesimals. But yeah, like I read, which I didn't know, that like Leibniz really was trying to explain calculus in a way that other people would understand it, they could extend it, and Newton really didn't have that as a concern. He was just
Well, they make the argument that
Yeah.
Leibniz formalized the notation.
Yeah.
They developed it after, but they give all credit to Newton because he was the first to get it on the ground.
Yeah.
Without knowing, and he's like, yeah, I clearly invented calculus, but it's like a patent office claim. It's like if you patent this great toaster, but someone names a toaster, who gets the credit? It's the same thing. It's like, they said Leibniz spent more time on the notation than our famous curly S, so he deserves the credit, but then they're like, Newton's the first to get it out, and quote unquote working. So but that's a fight that'll be not settled for the next couple of centuries, because they don't really know who gets all the credit.
yeah.
I think it's pretty settled. They say they both invented calculus independently.
It's pretty much settled. And in fact, Newton deliberately hid calculus because he didn't want the fuss. Like, Newton was a very strange human being. And, he only published the Principia under a whole lot of pressure from various people. And he really wanted to keep it to himself. He wanted to keep calculus to himself. And Leibniz invented it, and he got all upset because he said he invented it first, but he couldn't prove it because he was deliberately keeping it secret. So, it's like a bit of a mess.
So, why was he so secretive? About...
Well, because he was a paranoid lunatic. A genius, but also crazy,
That's Leibniz you were mentioning.
Huh?
Leibniz you said?
No, Newton.
Newton.
Leibniz was, from all accounts, Leibniz was a much nicer person to talk to than Newton was.
I read too that almost every sort of individual result of calculus was basically known to other people, like Fermat and it's John Wallis, they and Isaac Barrow, who was Newton's teacher, I would read, I was when I thought maybe Newton and Leibniz would be in this talk, well, although now they are in this talk, when I thought they'd be in this talk, I was like, okay, well, what did they actually do? And I was like, okay, this result is what they actually figured out, but oh no, Isaac Barrow knew that, and it's kind of interesting. It's, I think a lot of what they did was collect what had done before and just sort of streamline it and say, okay, well, this is we're going to take this subject which used to be you had to be a genius to come up with anything and just sort of make it a kind of an algebraic calculation.
Lots of people do that. Einstein did that with the special theory of relativity. Nothing
Yeah.
new in that.
Yeah.
He just put it all together coherently.
Yeah.
And at least one of Fermat's number theory theorems was formulated a few years earlier by someone else, but sometimes the famous person tends to attract all the credit or something.
Well, there's even a law by Stephen Stigler that every invention in mathematics and statistics is named for the wrong person. Including his, but someone else came up with that before him, and he gets all the credit because he put it in a famous book.
Yeah.
So yeah, so obviously this is not a great drawing, but so Tom was sort of alluding to there's another method that you can use to find this
Right.
area. And so you have like these triangles here, and then you keep bisecting. So you bisect horizontally. I'm sure this is not great. So like, so you first take the midpoint here, and like find this triangle, then the midpoint here and find this triangle, then this triangle. And it turns out that like if you add up the areas of the successive layers, that's a geometric series. And Archimedes just summed that series. So that's a thing which he just sort of figured out.
Yeah.
Okay. So I did want to, oh, my, oops. Well, I should have been trying to get this to work while I was. Oh, okay. Well, I guess this is. I had a website here, which I guess is not coming up. But I'll just mention that he also used his law of the lever to find the volume of a sphere. So there would be if things were working correctly, or there would be like a very confusing diagram right here. But unfortunately, I can't point to this diagram, so you have to believe me. And he did the same sort of thing where like he has a cylinder. Well, maybe I'll just draw my own.
There is Wi-Fi here, so is there some way you could go to a web browser?
Okay, let's see. Well, I can actually. I mean, this app is actually like good enough that like it can have a web browser like in the presentation, and so it should record this as well. Let's see what happens. Okay, so let's Archimedes sphere lever. Let's see what happens. Okay, this is kind of right. So, oh yeah, actually this diagram is a lot more clear than the one I had before, so this is good. So yeah, so he has a fulcrum here, and without going into the numbers, because it's actually, from what I can see, it's actually sort of an annoying calculation, although it's elementary in the sense that it doesn't require anything besides the Pythagorean theorem, but it's a lot of algebra. But so he has a cylinder lying on the fulcrum, lying on the lever in the same way that the triangle did in the previous slide. And then here he has hanging a cone and a sphere, and he knows from Euclid, I think, that the volume of the cone and the volume of the cylinder, and he can use this to determine the volume of the sphere. And then I think he also published this with some other method, although I don't actually know what his approximation method is for this sphere. I'm not sure what that was. Do you know?
You're talking about volume?
Yeah, the volume of the sphere.
I know maybe more about the surface area stuff, but not the volume.
Sorry, are those bold green lines like what the centroids would be if they were lines instead of points?
I actually don't know. I'm guessing what it is it's showing he's comparing this slice with this slice and this slice, so these are just supposed to be generic slices.
All right.
That's my guess.
Okay.
But I'm actually not sure.
And I guess this is also from that recently discovered, like 100 years ago discovered manuscript or something
Yeah,
like that.
yeah. And I did see I don't know if you guys ever watch The Great Courses. It's like an app with I don't know, some good teaching lectures. Although it's a paid app, but they have like a calculus course, and like on their lecture, the guy actually physically puts cylinders and cones on a fulcrum, and this actually works. It will balance. Okay. So this is another way of showing. I think I can switch back to the other thing. Okay. So there's this guy. This guy is a pretty interesting blog actually, and another sort of infinitesimal argument way to show what the volume of a sphere is, which is simpler than the one that uses the law of the lever, but it uses the same ingredients, is to show that a sphere has the same volume as what this guy calls a vase or a vase, which is a cylinder with a cone taken out. And you can actually I think this is simple enough that I can just sort of do it. So if the sphere has radius r, and you're looking at a slice at height h, this is r. So then this distance is the square root of r squared minus h squared. And so the volume of the slice is pi dx r squared minus h squared. And then over here, the if you just take the volume of this cylindrical slice, that's pi dx r squared, because the cylinder has constant radius r, it's always the same. And the cone has, which is being deleted, has volume pi dx h squared, because the cone sort of linearly goes down to a point. And then these are equal, because you can just expand. This. So you can combine Archimedes' ingredients, which you use with a lot of lever, to actually give it a little bit of a simpler proof than Archimedes had. And there's also so that's pretty cool. Actually, the main reason why I wanted to show you this in particular is there's like this guy had. Actually, let me just delete whatever. Oh, whoops. He has like this pretty cool GIF of showing that if you take a sphere and you put a cone in, it equals a cylinder. So that's kind of neat. Okay. And so one last one, which I will tell you about once I search for it, is this is also, again, like, so these all have the same structure in terms of infinitesimals. I'm kind of just telling you about this because they're cool. But then we'll get back to like the infinitesimal stuff pretty soon. So there's this theorem called Archimedes' hatchbox theorem. So if you take like a sphere and you take two parallel planes and you slice the sphere like this, then the surface area is only dependent on the distance the planes are away. It's independent of where they are. So you can like slice, you can take two parallel planes like a mile apart and like slice along the equator, and you'll get some surface area of the Earth, counting the ocean, of course. And that's actually equal to what you get if you do it at the very top and just get like the slice of the North Pole. I found that to be pretty surprising. And you can also, and you know, so I didn't go through it, but you can actually do an infinitesimal argument for this, where you have the slice be infinitely far apart, and then this part of the circle, the sphere, is just a slice of a right cone. Sorry, right here. Which you can find the area of pretty easily. But again, it's actually kind of a lot of algebra. There's nothing more advanced than the Pythagorean theorem, but it's a little bit hard to go through all of it. Okay, so now I want to return to the idea of making arguments of this form precise, but still maintaining the fact that they involve infinitesimals. And so I want to now kind of say more explicitly what the pattern is, except up to the fact of actually defining what an infinitesimal is. So the idea of all these things is you have some sort of process which is continuous in some way, or which can be arbitrarily divided, like finding the area of the circle by, cutting out as small as you like, or finding the volume of the area of the paraboloid by, slicing up a slice and comparing it with the corresponding slice on the triangle, and so forth. These are all these all sort of fit into this mold. And so now what does an arbitrarily divisible process mean? Well, it means you identified some function that's additive, in the sense that if you think of b of u and v as meaning the process from u to v, then that's equal to the process from u to w and the process from w to v for any w. And you've also identified some numbers that you, so you're trying to compute b from a to b. And then you analyze an infinitesimal division of this. You look at the process from x to x plus dx. And if there's some number such that for all infinitesimals and all x, you can conclude that this is equal to c times your infinitesimal when you're neglecting differences in the way we described earlier, then you're allowed to say, okay, well, the whole process is just c times b minus a. And after I made this slide, I originally didn't want to say it in the full generality, but I think actually it's a little bit clearer if you know it. So like, it can also, it doesn't have to be a number, it could actually be a function. It can also be a function. So, or a function h of x, then here, h of x dx, and then here, this is the integral from a to b of h of x dx. And I think it's maybe even a little bit clearer to say it that way, except for I didn't want to assume people knew what integrals were, so I said it where h of x was a constant. But if you do know what integrals are, maybe this is a little bit clearer way to say what's going on. Okay, so this is the pattern, and this is now up to what this word infinitesimal means. It is a thing which could be true or could be false. And once we define an infinitesimal, it'll turn out to be a true thing. Right, so here I'm showing. I think this is hopefully clear. So I have some slides saying what these steps mean in terms of the circle. And so here, the arbitrarily divisible process in the case of the circle is, okay, well, I'm going to take two angles, theta 1 and theta 2, and I'm going to let b be the area of the circular sector. And this is going to be good because if I take a equals 0 and b equals 2 pi, it's going to be the area of the sector all the way around the circle, which is what I want. And when you analyze an infinitesimal increment, you get this infinitesimal circular sector like we talked about earlier. And you do your Kepler magic and say, well, this is actually a triangle. And it has height r and base r dx. So this is r dx times r over 2. So c, which has to equal c dx, can be r squared over 2. And then you win, and you say, okay, r squared over 2 times 2 pi minus 0 is pi r squared. Okay, so now let me tell you one way to formalize infinitesimals. And so I mentioned in the meetup description that I was hoping to go over different ways. There is actually like a whole bajillion number of ways to formalize infinitesimals. I had no idea. Like when I signed up to do this talk, I thought I knew everything. Turns out I didn't know what I didn't know. There's a lot of systems of infinitesimals. But this is definitely the most famous one. And if you ask a normal mathematician if they know of a system of infinitesimals, it's rigorous still. If they know of one, they probably will know this one. And so it's an axiomatic, it can be given an axiomatic presentation. This set of axioms I'm going to give you is by this guy, Kepler, who wrote a calculus book based on this, has been teaching like calculus to freshmen using infinitesimals for a number of years. And okay, so these are not the only axioms. I'm going to give you 3 axioms first. And it turns out like a lot of systems obey these axioms. And I'll explore those. And then I'll give you there's 2 more axioms. There's a total of 5 axioms. Okay, the first axiom is actually more of a definition or something like that, or more of like just telling you some notation. So it's that R is a complete ordered field. And if you don't know what that means, it means that R is the real numbers, including all the rationals, including pi, including e, including minus the square root of 2, not including I, and not including any infinitesimals besides 0. So it's just the usual set of real numbers that you might think of. Okay, and the second axiom says the hyperreals, which is the system that we're interested in, is an ordered field extension of R. That means that every real number is in the hyperreals. There's 3 in there, and there's, a billion in there. And it has basic arithmetic operations and a relation that are extensions. So 2 plus 3 equals 5 in the reals, and 2 plus 3 equals 5 in the hyperreals. So that's good. And there's a list of like, so what this means, what ordered field means, so there's a list of like 10 laws, like distributivity of multiplication over, oh, actually, by the way, can you tell me if I might lose track of time. You should tell me if I stop.
I think it's fine.
Okay. Yeah, so like these laws are true, and there's like if A is less than B, then A plus C is less than B plus C, so some basic things. Okay, and there's the important one, or pretty important one. There's an infinitesimal in this. That means there's a positive number that's less than every positive real number. So it's not less than every positive hyperreal number, because it's not less than itself, but it's less than every positive real. And there's a picture of it here. Maybe I can zoom in. I think this might be. So here we have. So here is the number 0. It's got a whole bunch of infinitesimals around it. This number epsilon, minus epsilon. There's 2 epsilon. It's epsilon squared. There's minus epsilon cubed, and so forth. This is sometimes called the halo of a number. All the infinitesimals close to that number. I think Leibniz also called it a monad. Every number has the same. Well, every number has its own halo or its own monad. 100 has the same, the same structure of infinitesimals around it. And all these numbers that are collected around real numbers, these are all finite. But because we still have division, we can also do 1 over epsilon, and that's going to be an infinite number. And we can take minus 1 over epsilon, that's an infinite number. And it's not drawn here, but these numbers all have their own halos around them as well. Okay. I put this, by the way, just in case, I put this picture on the next few slides in case people want to look at it. This is from Kiesler's calculus textbook. Okay, so just to fix terminology, so a number is infinitesimal if, as I said, it's less than all positive reals. I forgot to put positive, I made this line. It's finite if it's less than some real number. So all these things are finite, including these ones. Epsilon's finite, 100 minus epsilon is finite, even though it's not real. They're all finite, and they're infinite if it's greater than all reals. So these are infinite, and these are all infinite.
So I have a question.
Mm-hmm.
So if the halo around the halo of infinitesimals around 100 is going to be less than, let's say, 50.
What do you mean? So all these numbers are going to be greater than 50, for example.
So if the absolute value is going to be less for all y in reals and 50 is in reals, then the halo around, how would the halo?
Oh, so 100 minus epsilon is not infinitesimal.
Okay.
Minus epsilon is infinitesimal, and epsilon is 100 minus infinitesimal. 100 minus epsilon is infinitesimally close to 100, but it's not infinitesimal itself.
That was just the difference.
Yeah. Yeah, and so this word finite encompasses all these numbers as well. So these are finite, even though they're not infinitesimal, and they're also not real. They're not real numbers.
So 2 different infinitesimal numbers
Mm-hmm.
are not the same, right?
Yep, that's right. Yeah. And there are other systems where there's just there are other systems where there's just one infinitesimal.
Okay.
That's not this system. Other questions?
How early did mathematicians start thinking in these terms? How far back does this go?
Well, so this particular system was invented in the 1960s by a guy named Abraham Robinson, and but people have been thinking about these systems for a while. And actually, there's like a historian of mathematics who's interested in infinitesimals who makes the point that like a lot of people think that, people use infinitesimals, they weren't rigorous. Then limits came around, everything was okay, and then finally somebody came up with a weird way to make infinitesimal rigorous again. And his point is that that's not accurate. There's actually an unbroken stream of work on making infinitesimals rigorous, that's gone on for the last 100 years. And it's had like varying degrees of success and varying degrees of popularity, but people have been working on it basically continuously. Other questions? And so this is what I said. So, so two numbers are infinitely close, maybe infinitesimally close. I'm not sure. If their difference is an infinitesimal, so this is not infinitesimal and this is not infinitesimal, but they're infinitesimally close or infinitely close. And then, as before, so two elements are equal or infinitely close compared to some other dx if their difference over dx is infinitesimal. So, for example, so epsilon is infinitesimally close to 2 epsilon, but it's not infinitesimally close with respect to itself, to 2 epsilon. However, it is the case that epsilon squared is infinitesimally close to 2 epsilon squared with respect to epsilon. I hope that makes sense or is clear. Mm-hmm.
The subscript to the squiggly equals a little bit like strength of a magnifying glass, isn't it?
Yeah, that's right. Yeah, actually, like there's that he uses that exact analogy that this. Well, actually, he uses the analogy of microscopes. These can be thought of as microscopes, where you're like zooming in around a particular thing. And so, if you're zooming around epsilon, like, can the microscope distinguish between those things or not? And so, it can distinguish these two things, but it can't distinguish these two things. And then he also has this analogy of like telescopes. You can use a telescope to look at an infinite number or a negative number. Other questions? Okay.
So the sum of two infinitesimals are also infinitesimal necessarily?
Yeah, that's right. Okay, so there is a calculator which I linked to for a system, which is not the hyperreals, but it does obey all the axioms which I presented so far. And which also is no longer here, so I will have to search for it. Maybe I can just search for this calculator. Okay. Yeah. Okay. So this has an infinitesimal that it's called D, and I will first let me see. Maybe I can zoom in. Okay, so I'll first define, so the infinitesimal is called lowercase d, and I'll first define a capital D because my iOS keyboard keeps capitalizing the first letter I type, even though I turned it off. I'm not sure why that happens. So there's, so this is infinitesimal. So if I type in something like this, it says, okay, that's true. And I can get an infinite number by doing this, and I'll also do this just in case. So right, so if I take, I don't know, I can do things like 1 over 1 plus d, something like this. It's going to expand it. This is actually not, it's like an approximate. This is actually an infinite. So I can do that. And the kind of the point I want to make, so this is a system, it's totally consistent, it's totally concrete. You can put it on a calculator, you can put it on a computer. And the downside of this system is that all that's guaranteed to be here are the functions which I told you about already, which is plus, times, and divide for if your number is non-zero. And that's not enough. That's not enough to do calculus, that's not enough to do mathematics. So the problem is, how can you define a system which implements the functions that you need? And in this case, it does go beyond that. Am I back there? It does go beyond what's okay, I'm going to use a trick where it capitalizes the first letter, and then I type what I want, and I go back and delete the capital letter. And it does provide other things. It does provide every number has a square root in the system, which is nice. But for example, the infinitesimal has you can take the sign of it, but if I try and take the sign of an infinite value, it says I can't do it. So not every function that you want to take on the reals is defined in the system, and that's kind of the trade-off. Like this is totally concrete. You can understand the representation. You can program it. But maybe not every function is defined on this system. And this is actually an interesting puzzle. You can actually figure this out based on what I've told you so far. So I wonder, so the puzzle is, so recall that h is infinite. And the puzzle is to figure out if square root of h plus 1 minus square root of h, is that infinitesimal? Is that finite? Is that infinite? And you can actually deduce this. And I was planning to just demonstrate this in the calculator, but it turns out that like there's some sort of bug, or maybe it's a bug in Safari or something that comes up with these nonsensical null exponents. That's not the right answer. So instead of actually demonstrating it, you can sort of figure it out, or you can just ask me. I'll just tell you. Cool. Okay. So I hope that motivates the definition, which is in the hyperreals, we don't want to have this problem. So in the hyperreals, we want to say every single function you could possibly define on the reals can be lifted to the hyperreals. So sine can be lifted, e to the x can be lifted. If you define if you define a function which is one on the rationals and 0 on the irrationals, that can be lifted. So the next axiom says every function that exists can be lifted to a function f star on the hyperreals. I actually didn't say this is on the hyperreals. That's kind of the crucial thing here. Oh yeah, no, hyperreal function. Yeah. And the third axiom says they have all the same properties. Meaning, if you compose these things to get a system of equalities, so if you compose these things and form equalities and inequalities between them, then those are preserved, and also conditional systems are preserved. So what does this mean? So it means that, so for example, sine squared of x plus cosine squared of x, that's true in the reals, so it's true in the hyperreals. And this conditional thing here means that you can also form conditional statements. So x greater than 0 implies e to the x greater than 1. Hopefully that's true, or I'm embarrassed. And so that's true in the reals, so it's true in the hyperreals. And this is actually extremely powerful because of the fact that you can lift any single function at all and you can combine them in this conditional way, it turns out to be extremely powerful. And so the cool thing is that there is actually such a system of numbers. And the good news that I'm here to tell you today is that with this system, the heuristic which I presented is actually a theorem. And so this guy I mentioned, so Jerome Kiesler wrote a calculus textbook for freshmen, and he also wrote this, which is kind of a companion for more upper level students or something like that. And so he calls this the infinite sum theorem. I don't think anybody else calls it this, but this is a theorem which says exactly the heuristic, which I was saying that is used by Kepler and is used by many other people. So it says that if b is a function that's additive, which is what I call the arbitrarily divisible, and you analyze each infinitesimal increment, and it's c times dx, then it's just true. So it turns out that all these things, neglecting these small changes, it's actually like, it's just valid, which is cool. And that's kind of what I wanted to get to. There's about 100 hours worth of like previous, like further directions to go into. One thing which I was hoping to make a real part of this talk, but it turns out it's just too long. To just go through it's too long. Is that Euler also used infinitesimals, but he used them in a totally different way. There's just like a different principle involved in the way that Euler used infinitesimals than in the way I just described. And just to give you a glimpse of it, although I'm not going to go through it. So he wrote this is like essentially a pre-calculus textbook where he's not assuming anybody knows calculus, but he's just saying, okay, just know algebra, that's fine. And he's analyzing a to the x, and he wants to show that it has this form of some infinite series. And so he splits up x into an infinite number and an infinitesimal number, moves this infinite number outside, does some shenanigans, and now he has like a number raised to a power. This is supposed to be an integer, even though it's infinite. So he just expands it with a binomial theorem. Then he goes term by term and says, oh, well, k minus 1 over k, that's infinitely close to 1. I'll replace it with 1. This is also infinitely close to 1. I'll replace it with 1. And the question is, how do you know that if you make an infinitesimal change in all the terms of an infinitesimal sum, that you get something which is the same? And it turns out that Euler he used these all correctly. Like there's actually a principle, it's a theorem which you can state, which just covers these uses of infinitesimals. And is actually like where I got this from. I actually like I just like copy and paste it from somewhere. This is an article which was in Mathematics magazine, and it won some writing award. It's like a very good article. If anybody's interested, I'll give you a link. It just analyzes. It's pretty readable too. Analyzes this use of Euler use by Euler of infinitesimals. So as I said, this is sort of just scratching the surface. These infinitesimals also give you a new way to look at some facts from real analysis. For example, you may know if you've taken, I think, calculus or real analysis, that there's an epsilon delta definition of continuous. With the hyperreals, that gets changed into, if you have two infinitesimally close values, then they're f of those things are infinitesimally close, which I kind of alluded to before. And this is like a theorem that this definition is the same as the normal epsilon delta definition. There's similar ways to give these sorts of versions for many other things, for differentiability, for uniform continuity, for continuous differentiability, for functions uniformly converging to another function, and so forth. And you can give new proofs of existing theorems. And actually, I think I don't want to say too much about this, but I'll just say you can give new proofs of existing theorems.
That one?
Uh-huh.
The theorem on top, is that really like rigorously stated? I don't quite, it seems kind of, or is it sort of approximate? I don't quite. So
it's rigorously stated, except for I'm like sloppy with these. So this is like the lifting. It's unfortunately like common to like drop the star. So this function is say a function from R to R. This is the lifting of that function from the hyperreals to the hyperreals. But with that, it's rigorous.
Well, the approximately equals, isn't that kind of a slippery?
No, this is why I define it as infinitely close. This means that.
Oh, I'm sorry.
This minus this is an infinitesimal.
Oh, okay. All right.
Any other question? If you know anything about topology, this is not related to this is not constricted to real analysis. You can also do these things on any topological space. You can get the same translation where instead of using the analog of epsilon delta for topological spaces, you can just use the exact same thing. Infinitely close things get mapped to infinitely close things. That's what continuous means. And then so if you know what a compact is, there's another definition which is perhaps clearer with non-standard numbers. Same thing for open sets and various other topological notions.
Question.
Yeah.
Can you go back 2 slides?
And this is like a whole bunch of other stuff. It's like so I read something about these two. That's okay. That's something. This I tried to read. I couldn't understand it. This I've never tried to read, but I've heard about. It's just like a bajillion fields. Actually, I don't even want to talk about this slide. There's also like questions about. So R star has a structure to it. You might ask, what is the structure? Like, can I say more about how this is structured? And there's been like a lot of interesting work about that as well. And that's my last slide. So that's it.
So,
Now we just talk, I think.
okay, well, of course, is it infinitesimally different from one?
Well, so it's still the case. So yeah, like in like normal mathematics. So yeah, so 0.999, etc. You know, is interpreted to be essentially a limit, which is equal to 1 in the real numbers. And it's still the case that if you take that limit in the hyperreals, it's still equal to 1. But something which is true is that in the hyperreals, so you know, here we have a decimal point, you know, decimal place at place 0 and place 1 and place 2 and so forth. In the hyperreals, it actually is, so you have a 0th decimal place and a first one and a second one and so forth. And then over here, there's like an infinite one. I'll call it n. And there's, so maybe this is a 9. And there's also an n minus first.
So n is like the last decimal?
No, there's still no last one, but there are infinite ones. This is the same sort of thing where like you have like, so yeah, there's no last one still, but there are infinite ones. And there's, so like n squared is another one. The floor of the square root of n is one over here.
Isn't that these 0 and 9 are rationals, right? And the 1 is like a natural number. So that's why there's this distinction.
So like if you take like 0.99 like a finite number of times, that's going to be like a rational number, and that's going to like converge to 1, which is why like they say like, you know, well, if this 0.9999 with dot dots, that means this limit of the rational numbers, which converges to 1. But anyway, so
aren't there n9s in the non-hyperreal, in the regular real?
So this n is greater than every natural number. In addition to like infinite reals, there's also infinite natural numbers.
Okay, like non-countable, uncountables.
They are uncountable the way I stated it, although you could also have a system where they are countable. But yeah, so yeah, the way I presented this system, it's uncountable. That's right. Anyway, so you could imagine an interpretation for 0.99 with you know, repeating as meaning there are 9s in every natural place, but there's some infinite numbers that don't have 9s, and there it would be less than 1 by an infinitesimal amount. So I mean, that's an interpretation. Yeah, sure. But it's still the case that if this limit in the hyperreals converges to 1.
Well, all right, and any other conversation or any other topics, anybody?